Hi. Today we're going to continue on talking about Chapter 10. We're actually getting pretty close to the end of things, so let's get started. As a brief warm-up, I want you to take a look at these two problems. You can read them there. You can hit the pause button to go through them, take a minute, absorb them, at least try and get a setup because I'm clearly showing you two different scenarios so that you can get that practice. Okay. I'll get started. I'm assuming you paused. For the first problem, we are talking about a weak acid. So we are in a buffered region because right now the equivalence volume should be 10 milliliters and obviously 8 is less than 10. So the guiding formula for it being a buffer is going to be equal to pKa plus log base over acid. Remember from the last video, we're going to shortcut the process, and instead of using moles of base, moles of acid, which is already a shortcut, we're just going to talk about fraction of the titration completed, or a ratio of equivalent, so to speak. So this would be equal to 3 plus log of, eraser. 3 plus log of 8 over 2 because 8 milliliters of base have been added. 2 would be remaining to be added to get to our 10 of equivalence, and that should come out to be 3.602 as our pH. For the same situation, if pH or if HA was a strong acid, instead of going through it as a buffer, we would just figure out the concentration of H plus remaining, which would be equal to the initial concentration times the fraction of the titration remaining. In this case, it'd be 2/10, times a dilution factor, our initial volume being 10 milliliters, our current volume being 18 milliliters, and that should give us 0.0111 repeating molar, and that pH would be equal to 1.954, which then is consistent that a weak acid strong base titration at the same point would give you a higher pH value than a strong acid strong base titration because, well, the acid's strong. So for a frame of comparison, this is the same problem as the previous slide. So your answer would be 3.602 as your pH. But what if your weak acid was diprotic? Obviously, the math should be different at least some of the time, if not all of the time. So how do you figure out the pH at 8 milliliters if the base of base being acid, and at 11 milliliters when we knew that the equivalence volume in this first problem is 10 milliliters? So at 11 milliliters, is that excess base? Is that not excess base? How does that all work? That's what we're going to take a look at today. So to get us started, I found this image and I thought it would be beneficial to talk about it a little bit. This is the general curve for a diprotic titration. A couple things you can notice. The first thing I'm going to point out is that this is completely not to scale. I have a to scale image we're going to look at in a couple slides. But just to relate the fractional composition to the titration curve. The idea is that over here, before we've even started, our solution is predominantly H2A. As we add base, the H2A reacts with the added hydroxide of the strong base in a one-way reaction to make HA. So what we're going to see is the H2A the fraction goes down, the HA concentration fraction goes up until we reach our first equivalence point. Now, this is going to be the guiding principle for the rest of the video. Once we reach that equivalence point, what really ends up happening is that H2A is the predominant situation. Like, that's the predominant form of the acid, and you don't really get conversion of HA into A2 minus until you get 100% conversion of H2A into HA. The real big reason behind that is that everything kind of balances back out in terms of equilibrium. So if you were to, say, have an HA particle react with the base to make A2 minus, equilibrium reestablishes, your pH is still fairly acidic, and when all dust settles, you've got predominantly H2A and HA minus in your solution, so it all kind of balances out. The numbers that we're seeing on the bottom here are the equilibrium fractions. So we're kind of dropping it, like putting in a little bit of base and letting it mix and equilibrate before measuring the pH, or I guess in this case, calculating the pH. Don't forget that here, this is the first half equivalence point. Remember how I said this is not to scale? Yeah, because like the part up to 4.4, totally, that distance totally equal to the part after that until the first equivalence point. But then we can also see that there's this second point where they cross, and then at the second equivalence point, now most of the solution is in the form, oops, I'm just going to erase that. Most of the solution is in the form of A2 minus. And so that's the general pathway we're going to be taking with this. We're going to dive in and look a little bit more specifically. Now, your book prefers to go through this in looking at the base side of things. You're getting a weak base and you're titrating it with a strong acid. We're going to go through the same, like all the steps, and I'll explain as we go, but hypothetically, if you kind of understand how to do one way, we can do the other way. Titrating a base with an acid and titrating an acid with the base, all the numbers are processed the same. You just have to think at each step of what the solution looks like and how that solution, with what it looks like, behaves. Which is exactly what I said in the previous videos about this. So the two reactions that'll be displayed is, instead we're saying base B, and it's dibasic, so it has the propensity to react with hydronium ions to make this species BH+. This is probably some sort of an ammonium species, but this molecule has two such ammonium moieties, allowing it to pick up a second proton and to make this particle BH2 2+. This would be analogous to our H2A, this would be analogous to our HA minus, and this would be analogous to our A2 minus, and we handle it all in the same exact way. Remember that these formulas, these chemical reactions, are based on particles and therefore based on moles, and so that actually gives a little bit more clarity to the process, because this one is to scale, and what you can see is that the first equivalence point here, if we draw a line down poorly, we have about 1 mole of HCl added, and then at the second equivalent point you have 2 moles of HCl added. This is obviously a titration of a known diprotic base or dibase, carbonate, so the carbonate ion will react with H+. I'm giving the net ionic reaction to make HCO3 minus, and then HCO3 minus will react with H+ to make H2CO3 minus. Now it's showing moles in the bottom, but moles of acid is just equal to molarity of acid times volume of acid. And so since the molarity of the acid that's added is a constant, you could just as easily have made your x-axis volume, and the curve would look exactly the same. It would have the same shape and the same general features. This means that, well, technically it means that the amount of volume you need to get from the first equivalent to the second equivalence point is equal to the amount of volume you need to get to the first equivalence in the first place. So I think a good process, a good step in this process to have is to label 2 volumes. We're not just going to have VE, we're going to have VE1 and VE2, and we're going to define the 2 such that VE2 equals 2 times VE1. The idea being is that the number of moles needed to convert carbonate into hydrogen carbonate is equal to the number of moles needed to convert hydrogen carbonate into carbonic acid. And no, I did just notice H2CO3 does not have a negative charge. That would be silly of me. Thank you for pointing that out. But in general, there's this repetitive process to it where once you understand what you're looking at, it's just the same set of calculations again with just slight modifications from the first time you did it. So let's take a look at a problem and hopefully this will start to make a little bit more sense as we go along. So we have our hypothetical base B that picks up 2 protons. They're telling you that based on the fact that there are 2 pK values, pKb values, and they're telling you it's dibasic, so no need to do any guesswork. Obviously, to calculate VE1, this is going to be equal to a VA, because we're adding acid. So VA is equal to MBVB over MA, which in this case, so that would be 0.1 times 10 milliliters over 0.1. Why am I writing all of this? This is pretty solid mental math. This we can also use to say then VE2 is equal to 20 milliliters. So we're building a hypothetical curve, nice and straightforward, hopefully very clear that it's just after 10 milliliters we've reached the first equivalence, and after 20 we reach the second. So we can kind of already picture this general, curve, and it should look very similar to the curve on the previous slide where the drops are evenly spaced, and this would be 10 and this would be 20, and hopefully we can calculate every pH in the middle. So let's start. Region 0, no acid added. So in our hypothetical beaker, all we've got is a bunch of B. B, 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 B. But we don't have a bunch of B because they tell you B is a weak acid. And so we know that B reacts with water to make a small amount of BH plus OH minus. My equilibrium arrows are not looking good today. So there will also be a small amount of BH plus, and there will be a small amount of OH minus. It's so small it's like coming over the top of the solution. But what we've written here is analogous to KB1. This is the first protonation, which we'll get to in a second. That's for the later slides. But in that case, we know that the generic form for the fully deprotonated form of any polyprotic acid, it's KB1, is equal to BH plus times hydroxide over B. And then through some systematic treatment, we get to x squared over F minus X. So in this case, we're going to use the KB1, so 10 to the negative fourth equals x squared over 0.1 minus x. X equals hydroxide, which is equal to, I wrote this down so I wouldn't have to remember, should be equal to 3.11 times 10 to the negative third molar, and then that would then yield a pH value of 11.49. So we've got our starting point, logical starting point, starting with a weak base pH largely over 7. We start dropping in a small amount of acid, and as we drop in acid, we're slowly going to start to a decrease in pH, and we enter this downward sloping line, which is a buffered region. So in region 1, we've got any volume in between 0 and the first equivalence. And what the solution is going to look like is, in general, we've now got some B and some BH plus. Now there's 2 ways we can just describe this solution. Obviously, this solution is governed by the KB1 equilibrium, but look, I have a real problem with using the Henderson-Hasselbalch equation with POH and PKBs. It just serves to confuse me. Yeah, you can do it. Everything's flipped. POH equals PKB1 plus log of acid over base instead of base over acid. But I find that confusing. I'd rather take this and I'd rather spend the energy at each step to translate everything into acid to make sense of it, rather than like accidentally flip one equation or use one wrong number. I mean, yeah, it's another level of thought, but I feel like it works better. So the governing equation here, this, if we consider that our fully acidified form is BH22+, our intermediate is BH+, and our fully deprotonated is B, this buffered system is actually using these 2 forms, which would be governed by Ka2. Keep in mind that the first protonation and the last deprotonation are related. So we know that K2 plus, or sorry, PK2 plus PKB1 equals 14. So our PK2 here we're going to use is 10. Our PK1 is going to be 5, but we're not going to use that yet. Now, hopefully this makes a little bit more sense. This should look a little bit more familiar to stuff we have tackled before. For each of these, the generic form is going to be pH equals PK2 plus log of B over BH plus. And this is still consistent with what we see before. We're going to take the step of making our life a little bit easier, and since our equivalence volume is 10, we're going to set up our ratio of base to acid based on volume added versus volume remaining to get to 10. So for 1.5, pH is going to be equal to, sorry, that's 10, I almost wrote 5 for some reason, plus log of 8.5 over 1.5, and that equals 10.753. For the second one, pH is going to be equal to 10 plus log, log looks like 10 grams. I'm having a good time today. 5 over 5, and of course that's going to be equal to 10. So again, we're going to see, well, I'll get to that in a second. And then for the third one, pH is equal to 10 plus log of 8 over 2, which, base over acid, no, 2 over 8. See, this is the problem. I trip up with this too, because if I'm not constantly like trying to keep it in mind, I will make these mistakes. But obviously we're almost done, so there's more acid, less base. 9.398. This one's important to point out. That's right here, that first half equivalence point. So that's where if V equals 1/2 VE1, pH is going to be equal to a pK. Because we're titrating a dye base with acid, in this case, the first half equivalence point pH is going to be equal to pK2. If this was all an acid, it would be working differently with pH is equal to a different pK, but at half of the equivalence point, pH is still equal to a pK. If you think about it in the problem, you get different answers at different times, but that thinking is something I'm going to leave you to do. For the second region, that's where we've hit our equivalence point. So if we're working down our graph, we're right here. And as it says, that at the first equivalence point, we're going to define that as 100% conversion from B into BH plus. So if we were writing our ICE table, ICF table, what it would show is that we have a stoichiometric amount of B and H plus. We've got a 100% solution of BH plus. And our beaker is full of BH plus, except if we need to figure out the H plus concentration, well, then I don't know what's going on, because BH plus is an intermediate form of the diprotic acid. It's both an acid and a base, which means there's going to be a small amount of B and a small amount of BH2, 2+, which means there's going to be some H pluses floating around and some OH minuses floating around, and I don't really want to do the systematic treatment if you don't want to, so we can kind of jump straight to our answer. We know that for the intermediate form, the H plus is equal to K1 K2F plus K1 KW over K1 plus F. Now remember, we said this with the previous titration, with the weak acid titration, it was monoprotic. As you're adding base, you are diluting everything that's in your solution. If you're in the buffer region, that's not super important because it's a buffer, and buffers aren't really super susceptible to dilution, especially at concentrations of 0.1 molar. But now that we're at the intermediate, the dilution actually does have an impact. You see F has come back into our equations, and F isn't F anymore. This is not a 0.1 molar solution because you've added 10 more milliliters of liquid. So what I'm going to do is every time we have a new F in our equations, I'm going to add a prime to it. So a little bit of calculus for you, because that's what calculus is. It's just drawing a bunch of like little tiny primes. That's all it is. That's not all it is. My apologies to your math teacher. But we need to figure out what this is. And so I'm going to give you your formula here. It's a standard dilution formula rearranged. Basically, the new concentration is the old concentration times a dilution factor, which we saw in our strong acid, strong base titrations. So in this case, it's going to be 0.1 molar times our initial 10 over our current 20. And that gives us 0.050 molar. And so we're going to plug in, and I'm gonna translate everything into K1 and K2. If you could do hydroxide if you really want to, I think it would work, but I'm not 100% sure. If you want to hit pause and you want to figure it out with the hydroxides and then come back and see if we get the same answer, you can go ahead. But our formula here is going to be 10 to the minus, let's see, fifth times 10 to the minus 10th times 0.05 molar plus 10 to the minus fifth times 10 to the minus 14th over 10 to the minus fifth plus 0.05 molar. And I chuckled before because while I did write down my answers before, I made a fatal mistake and I got distracted and I didn't finish one of these, so I'm going to do it now. Numerator first term, 10 to the negative 15th times 0.05 plus 1 times 10, or 10 times 10 to the negative 19th, numerator divided by denominator, 1 times 10 to the minus fifth plus 0.05, and okay, I really hope, yeah, I like that number. Let's see how well I did. 3.165 times 10 to the negative eighth molar, which should give me a pH value of 7.4996, which, you know, if you do your shortcut of saying pK1 is 5 and pK2 is 10, and since this is pretty concentrated, you get an average of the pKs, which is in fact 7.5, which works. So that all does kind of pan out here. Obviously the numbers that are over here on the graph of carbonate, these are not the pK values for carbonate, which is why the pH value doesn't quite line up, but it would be similar, just with different numbers. So moving on into region 3, what is going on? Well, we did have 100% conversion into BH plus, and we keep adding acids, so now there's some BH pluses, and we're starting to build up some BH2 2 plus. Well, that's another buffer system. That we're right here. Where's my pen? We're right here, and we're in a new buffer region, except now this buffer region is governed by K1. So pH equals pK1 plus log of BH plus over BH2 2 plus. And again, we're going to do our shortcut. If you feel comfortable with the ICF tables, if you want to take the time to go through that, you can. I like the shortcut, especially if you end up doing it correctly. So I'm going to use the shortcut. Here pK1 is going to be based off of pKb2, so pK1 equals 5. So for the first one, pH equals 5 plus log of. The hardest part about moving into the second equivalent is that you have to treat the first equivalent in terms of volume like it never happened. I don't want you to use 12 over 20 or 12 over 8. Basically, the first 10 milliliters created all of the BH plus, and then the next 2 milliliters created some BH2 2 plus. So it's really like saying I added 2 milliliters to the BH plus solution. So in this case, I would be writing 8 over 2. You treat the two equivalents like they don't, like the other one doesn't exist. It's almost like you hit a reset button, like start again, do a new titration. because that's how the math ends up working out. And what you should get here is 5.602. For the second one, here we've added, since we're only considering the second 10 milliliters, we've added 5 milliliters. There's 5 left to go. Oh, look, that's going to be a 0 again. And pH for the last one is 5 plus log of 1/9, which is equal to 4.046. So again, this second half equivalence point is basically where your volume is like 1.5 equivalents. But since the first one doesn't happen in terms of our math, we're back to the halfway point. And again, pH equals pK, in this case 1. This is not, I mean, the volume 15 is not half of 10 and not half of 20. I'm just saying that's how it works out. That's how you do it. Moving on to region 4. We've now hit our second equivalence point in our beaker. We have a absolute metric load of BH22+. In fact, that's all we've got stoichiometrically. And therefore, we're going to basically treat this solution. It is chemically equivalent to dissolving acid in water in the first place. We have 100% acid, so all of your H+ is going to come from the BH22+, getting into a little bit of a back equilibrium to make BH+ and H+. So this is our K1 equation again, and we know that K1 is equal to x squared over F minus x, except F has come back. And now it's not the same F as before, because now we're added 20 milliliters, we're going to call it F double prime. There's two ways to calculate F double prime. You can either go back to your original F and use your initial volume over your total volume, or you can dilute down your prime by the volume that you had at F prime by your new total. I'm going to show you both really quickly. They work out the same way. We had a 0.1 molar solution. We had 10 milliliters. We added 20, which means we now have 30. If instead you have used your 0.05 molar dilution, we initially were at 20 milliliters total at the first equivalent. So that's 20 over 30, and we get the same answer. So using K1 equals x squared over F double prime minus x, keeping in mind that K1 is 10 to the minus fifth, F double prime is 0.0333 molar, x, which is H plus in this case, you should get out 0.0143 molar, and that should yield a pH value of 1.85. And as you can see, our pH is getting reasonably low at this point. At least I think. Nope, nope, nope. Those are both no. Those are the wrong answer. I am deleting that. It's just me getting ahead of myself. That's the next set. I'm going to go back up a step. 5.72 times 10 to the negative fourth molar. I was looking at that, like the pH there, that's a little low for the equivalence pH. 3.24. Looking up at here, I'm like, that's like 4. How did it get down? That makes a lot more sense. But our pH is going steadily down, steadily down. So finally, we're going to look at what happens as you're above the second equivalence point. This is, obviously, we're now in this territory over here. We have excess acid. So in this case, all we have to do is figure out the excess acid, and it's going to be just the same as we did before with the weak acid, with the strong acid, strong base titration, with the weak acid, strong base titration. The nice thing about this is that all excesses, every time you are over past the equivalence point, the pH is calculated exactly the same way. So since we have 0.1 molar, we're going to have 0.1 molar. The amount of excess at 35 milliliters, oh yes, is going to be equal to 15. I wrote 5 for some reason. Over, we had an initial, so that's 45. Does that make sense? Did I calculate right? I don't think I calculated it right. Because we were at 20, so we're 15 milliliters over. I think I did it for 5. Not having a great time with this. I'm going to fix it right now. 0.1, that's... Oh, yes, yeah, that's right. No, that's not right. Well, no, it should be right. 0.0333 molar. Does that make sense? 10, 45. Right, so we're 15 milliliters over because the first 20 went into the reaction. Yeah, no, this should make sense. I don't know why I'm looking at it like I'm crazy, but yeah. pH is equal to 1.477. I like it. I really hope the book agrees with me on that one. If I'm wrong, I'll totally put a comment below fixing it, but I don't really think we have to think about it too much. Oh. Yeah, that's wrong, though. Oh, I know what it is. I know what it is. Oh, this is right. The other, okay. I think it said 25 in the book. You can check that and let me know. I think it says 25 in the book. Doesn't matter. I sold it for 35 anyway, because I can do that. I just figured it out on the fly. Who cares? So, in summary, for polyprotic titrations, each equivalent is chemically and mathematically isolated. So basically that means consider all of the first equivalent by itself, consider all of the second equivalent by itself. Subtract it out if you get any numbers that pop in, but don't forget that pK1 plus pKb2 equals 14. pK2 plus pKb1 equals 14. Any F is subject to dilution. And honestly, if I'm given like my best advice, draw a beaker. Think about what particles are in the solution. You know whether or not something should be treated as a buffer or not, and you know whether or not, like, how to tackle solutions of different composition. Because that's all you got to do. You just got to sit down and you got to think. Thanks for watching.